So question number 1 was basically a properties of exponent question, and it's sort of a you either know it or you don't know it kind of thing. If you don't know it, you probably couldn't do problem number 1 or number 2, and that's an issue. We need to know our properties of exponents. They are, in review, a product property, which says if you multiply like bases, you can add the exponents. The quotient property, or the division property, says the exact opposite. When you divide like bases, you can subtract the exponents. The power property says if you stack exponents on top of each other, you multiply them. Negative exponent property, if you have a negative exponent, all that negative does is tell you to take the reciprocal of the base. And anything to the 0 power is essentially 1. So when it comes to simplification, I mean, there's lots of different pathways and avenues you can take. I'm not saying the path that I take is the only way or the best way, it's just what I'm going to do. So the first thing I notice is a parentheses with an exponent. So I'm going to go ahead and use the power property and distribute the exponent. Do note that anything that I do not highlight, I'm just going to recopy. So time to distribute the exponent of 6 in the denominator. That gives me p to the 12, q to the 18, r to the negative 6 times pq squared r to the 4. At this stage, I think what I'm going to do is I'm going to clean up the denominator. It's getting a bit noisy down there. And notice how everything is multiplying each other, so it's just an application of the product property through multiple bases. Now, one thing to note about the properties of exponents is that it only works for like bases. What that means is you don't want to mix up the letters. So just do, the p's with the p's, the q's with the q's, and the r's with the r's. Again, whatever I don't highlight, I'm just going to copy down. pq to the 6 over. Property says when you multiply, you add the exponents. So for the p's, you get 12 plus 1 is 13. For the q's, you get 18 plus 2 is 20. And for the r's, you get negative 6 plus 4 is negative 2. Next, I think we'll go ahead and do the quotient or the division property. So again, you do the p's separately from the q's. Now, technically, if you take a look at the quotient property, it does say a minus b, the numerator minus denominator. But what I like to do is big minus small. And I just have to remember that whatever answer I get, I put it wherever the exponent was biggest. For example, for the p's, you have exponents 1 and 13. Instead of doing 1 minus 13, I'm going to do 13 minus 1, which gives me 12. And since the exponent of 13 was in the denominator and it was the bigger exponent, I'm going to put the answer p to the 12 in the denominator. Same thing with the q's. The exponents we have are 20 and 6s, so big minus small would give me 14. And I'm going to put the answer q to the 14 in the denominator because that's where the bigger exponent was. Now, I've completely lost my numerator. And now things don't just necessarily disappear. You always have a 1 left over. Last but not least is to take care of a negative exponent, and all that negative exponent tells me to do is swing that to the opposite side. So my final simplified form would be r squared over p to the 12, q to the 14. Number 2 is the same concept. The only thing that's different is we have fractional exponents. And I hate to say it, but at this stage in the game, we can't be afraid of fractions. There's no running away from it. So either we get comfortable enough to be able to add, subtract, multiply, and divide fractions without trouble, or we get comfortable enough to know how to use our calculators to do it. Either way, I don't care how it needs to get done, but we need to not be afraid of fractions. So just like with problem number 1, I see exponent outside of parentheses, so I'm going to distribute first. So that's just copy everything down that I didn't work on or highlight. 4/3 over, and then distributing the exponent of negative 2 gives me y to the negative 10/3, z to the positive 2. Next, I'm going to clean up the numerator. I have the product property with the z's here. So this gives me x to the 3/2, y to the negative 2. And then for the z's, I would need to do negative 1 plus 4/3, which is negative 3 over 3 plus 4/3, which is 1/3. y to the negative 10 thirds z squared. Next, you have the quotient property with the y's and the z's. And again, I like to do big minus small. So for the y's, you would have to know that negative 2 is actually, quote, bigger than negative 10 thirds. So for the y's, I'm going to do negative 2 minus negative 10 thirds, which is negative 2 plus 10 thirds, which is negative 6 thirds plus 10 thirds, which is positive 4 thirds. Now, since negative 2 is technically the bigger exponent, and it was on the top, my answer of y to the 4 thirds will go on top. Lastly, for the z's, 2 is bigger than 1 third, so we do minus 1 third, which is 6 thirds minus a third, which is 5 thirds. So the answer of z to the 5 thirds will go on the bottom because that's where the bigger exponent was. Now, technically, we do have a radical in the denominator. We do have a fractional exponent in the denominator. But I didn't tell you to rationalize because you did enough work already. So this was an answer I accepted. To rationalize denominators, that's what question 3, 4, and 5 were all about. Now, the idea of rationalizing anything that involves radicals is to get rid of the radical. And it's based upon one simple idea: inverses. We should know by now that a square root and an exponent of square, or 2, are opposites or inverses of each other. A cube root and an exponent of 3 are inverses of each other. A fourth root and an exponent of 4 are inverses of each other, and so on and so forth. The question explicitly said rationalize the denominator. So my goal is to get rid of this radical in the denominator here. Well, it's a square root, so we should know that the opposite of a square root is a square. And quite literally, squaring something means multiply by itself. So all I'm going to do is multiply by radical 7 because I want to get rid of it. But of course, what you do to the denominator, you must do to the numerator. Multiplying straight across gives us radical 70 over, now remember, the whole point of rationalizing is to get rid of the radical. So radical 7 times radical 7 is just a plain old 7. So in the denominator, we have 6 times 7, which is 42. Now, you always want to simplify as much as possible. That's what the instruction says. So you want to see if you can simplify square root of 70. But, 70 is just 7 times 10. And that's just 7 times 2 times 5. There's nothing I can pull out. So believe it or not, that is as simplified as possible. Number 4 is the same idea, except we have a cube root instead of a square root. Now the idea is that an exponent of 3 will cancel out a cube root. Now take a look at our radicand here, the stuff inside the radical. It's a 5. We have just a 5. Now we want to cancel out the cube root of 5 cubed. We want an exponent of 3, which is just 5 times 5 times 5. Now this is not meant to be a hard question, but we've already said we have one of those 5s, right? So is it obvious to everyone that we need 5 times 5 to complete the triple? Or in other words, we need a 5 squared. So that's what we're going to multiply by. We're going to multiply by 5 squared. The only thing that's different or special is that since it needs to be inside of radical, we're going to multiply by the cube roots of 5 squared, top and bottom. So distributing gives us the cube root of 5 squared, which is 25, minus the cube root of 5 squared times 15, which is 25 times 15, is 375, all over. And again, the whole point of rationalizing is it gets rid of the radical, so that should just equal a regular 5. Now it comes time to simplification. The cube root of 25, I know I can't simplify because we're the one who used it. So we want to see if we can simplify the cube root of 375. And I hope everyone can see that 375 is just 125 times 3. And the cube root of 125 is 5. So this guy here takes the place of this guy there. So the final super duper simplified form is the cube root of 25 minus 5 cube roots of 3 all over 5. Number 5 is a rationalizing the denominator problem as well, but notice the radical is inside of a binomial. So in this instance, to get rid of a square root, we need a perfect square, but I need to square an individual term in a binomial. As far as I know, there's only one way we can do that, and that's to exploit this pattern here, that when you multiply two conjugates, it's the difference of the perfect squares. But notice how each individual term separate is being squared. A lot of people made this mistake. Oh, I need to square this, so I'll just go ahead and square that. But remember, the pattern for squaring a binomial, say a plus b squared, is a squared plus 2ab plus b squared. You get this extra middle term here that most people forget, but that's actually part of the pattern, and it actually screws us over when it comes to rationalizing because it creates more radicals. So the idea, if we want to get rid of the square root that's part of a binomial, you have to multiply by the conjugate. What you do to the denominator, of course, you got to do to the numerator, and just go ahead and distribute. So that's 30 radical 2 minus 3 times 2 is 6, because when you distribute, radical 2 times radical 2 is just a regular 2. Over. Now in the denominator, you can go ahead and certainly FOIL, but I mean, this is the reason why we use this pattern, because all it is the first term squared minus the second term squared. So the first term, 10 squared, is 100, minus the second term, radical 2 squared, is just a regular 2. So you get 30 rad 2 minus 6 over 98. Now when it comes to simplifying expressions that have both multiple terms, fraction, and radicals, the idea is you have to look at all of the coefficients, or all of the outside numbers. And you can only reduce it if every single coefficient simultaneously can be reduced. So the question you need to ask yourself is there a number I can divide up from all 3 numbers at the same time instead of 2 at a time? In this instance, the answer is yes. We can divide out a 2, so the most simplified form would be 15 radical 2 minus 3 all over 49. Number 6 is just a factoring quadratics problem, and I hate to say it, but factoring quadratics is not something you can calculate. It's not something you can it's not a procedure. It's not you do this every single time. It's a puzzle. It's thinking. It's logic. So you have to sort of know how to do it. It's one of those you know it or you don't know it things. And I hate to say it, but we need to know it at this point. However, I do have some tips and techniques and things to keep in mind to help things easier. So let's recall the idea. Quadratic trinomials are factorable into 2 linear factors, where whatever you put in these first positions has to multiply to the first term. Now, since it's just a regular b squared, we're sort of nice and lucky in that there's only one choice, b times b. That's the only factored form of b squared. Whatever I put into the last terms here has to multiply to this last number. Now, there are a lot of choices there, and to organize it, I like to what I call pairwise factor. What you do is you break down the number into two other numbers that multiply to it. So for 40, I always like to start with 1 in the number, and then increase from 1 to 2, and ask yourself, does 2 go into that number? In this case, yes, 2 and 20. Then from 2, go on to 3. Does 3 go into the number? No, so you skip it. Move on to 4. Does 4 go into that number? 4 and 10. What about 5? 5 and 8. What about 6? No. What about 7? No. The next number I would ask myself is 8, but if I've already written him down, so I know I can stop. These are all the pairwise factors of 40. You can stop when you go full circle. Reach a number you've already written. Now, what I do next is I take a look at this last symbol here. It's a minus, so I'm going to think of subtract. So this is what I'm going to be thinking about when I look at this list. I'm going to ask myself, right, what pair of numbers subtracts to the middle number of, and then I just take a look at the problem, and the middle number is a 3. And I hope it doesn't take a lot of thinking or guessing or figuring out that it's the last pair here, 5 and 8. Now I'm going to put symbols on these numbers, pluses and minuses, what have you. This is where the guess and check comes into play. This is the puzzle of the game. You go ahead and write down the blank numbers and set it equal to the middle number with the symbol. In this case, it's -3. And your job is to figure out, should it be pluses here or minus here? Pluses here or minus here? And now this is the guess and check part. This is where you just have to try it, and if it doesn't work, try something else. So for this particular problem, I hope it's not hard to see that in order to make this a true statement, you need a +5 and a -8. So those are the symbols, and this is the factored form. Number 7 is the same concept. The only difference is, the leading coefficient is not 1, but it should follow similar logic. Whatever I put in the first positions has to times the first term. Now, the first term is a 2x² now, so it's not a simple x and x, but rather 2x times x, because 2 breaks down into 1 and 2. Whatever I put in the last position has to multiply to the last number, 8. 8 pairwise factors into 1 and 8, 2 and 4. However, and the last symbol makes me think of subtract. But before I can start thinking, what pair of numbers, realize by putting a 2 here, when we eventually FOIL it out, this 2 will multiply whatever number I put into here. So this number will get multiplied by 2 eventually. So it changes my logic just a little bit. This is what I should be thinking. What pair such that, ST will be such that, what pair such that when I multiply one of them by 2 and then subtract gives me the middle number is 15. And there's no real way about it. You just have to try them all. Guess and check. You got to put some work into it. So I don't know what the answer is. So I'm just going to go ahead and guess the first one. Let's multiply the 1 by 2 and subtract. 1 times 2 is 2. Subtracting the 8 gives me 6. That's not what I want. Try the other one. What if I multiply the 8 by 2? 8 times 2 is 16 minus 1 is 50. Hey, I got it on the second guess. Sometimes you get lucky and you get it on the second guess. Sometimes it takes you the 5th guess, 6th guess. I've done problems where it takes me the 10th guess. You just got to stick with it until you get it right. So I know that the 8 needs to be multiplied by the 2, which means I know that the 8 has to go here and the 1 has to go here. But I still need to figure out the pluses and minuses. So go ahead and write down the bare numbers. Again, we're working with the 1, and we're working with the 8, which gets multiplied by 2 is really a 16. And I want it to equal the middle number of -15. I hope it doesn't take you a lot of thinking, but to make this a true statement, it has to be a +1 and -16. So that's +1 and -16. That's the correct symbols. Let me rewrite it all cleaned up. So the factored form of number 7 should be 2x plus 1 times x minus 8. Number 10, more factoring. The only thing about this particular problem, again, it's 2 binomials. This guy here is from the first guy. This guy here comes from the second guy. The only thing that's different about this problem is the leading term, 10. There's multiple choices. If you pairwise factor 10, it could be 1 and 10 or 2 and 5. I don't know which one's the right one. So, you just have to check both. That's just more guessing and checking. So it could be R and 10R, or it could be 2R and 5R. And then when you pairwise factor 9, 1 and 9, 3 and 3, you just have to go through both possibilities. So I'm not going to run through the spiel here. I think you get the idea. You just have to put in the work. You have to put in the effort of trying all possible combinations. If you were to factor this correctly, it ends up being, you don't need this one, but it's actually 2r and 5r, specifically 2r plus 9 and 5r plus 1. That is the factored form. Number 9 was sort of special in that it was, it's not technically a quadratic, but you should recognize that it follows the special pattern a squared minus b squared. It's the difference of two perfect squares. You're probably thinking, well, it's not a perfect square, it's a perfect fourth. Well, recall that x to the fourth is nothing more than x squared squared. So it is a difference of two perfect squares. This problem is just x squared squared minus 5 squared. And the difference of two perfect square pattern says if you have perfect squares and you're subtracting, it always factorizes into square root minus square root plus square root. So this guy should factorize into x squared minus 5, x squared plus 5. It's that simple. Number 10, I asked you to factorize 4 terms. And if I ever to ask you to factorize 4 terms, more likely than not, the technique will be factor by grouping. The idea of factor by grouping is you break this down into 2 smaller problems. The first 2 terms will be its own groups, and the last 2 terms will be its own group. And please note that I included the symbol with the second grouping. So when I rewrite this, I'm going to write it as 12n cubed minus 20n squared plus positive 21n minus 35. So this is you always put a plus here, and then this plus symbol came from the original problem. So just keep that in mind. By breaking up to smaller groups, instead of looking at the big picture, you're only looking at the binomials. And when it comes time to factoring binomials, the only thing you can really do is GCF, greatest common factor. So for the first parentheses, the biggest thing I can pull out is a 4n squared, which leaves behind a 3n minus 5. And in the second group, the biggest thing I can pull out is a 7, which leaves behind a 3n minus 5. Notice how these parentheses are the same. You want them to be the same. Because they're the same, we can go ahead and factor him out, 3n minus 5. And like with all factorings, you always put the leftovers in their own parentheses. And hopefully we can see that we have a 4n squared and a plus 7 left over. So that is the factored form for number 10. Number 11, multiplying rational expressions. I sort of said this in class during the lesson. When it comes to multiplying or dividing rational expressions, it's sort of ironic. I don't want you to multiply. I don't want you to divide. Rather, when it comes to rational expressions, 9 out of 10 times, it's all about factoring and canceling. So that's what we're going to do. We're going to factorize this piece, this piece, this piece, and this piece. So let's do this. The yellow, it's a binomial, so GCF. Biggest thing I can pull out is a 3, leaving behind a 5p plus 2. The light bluish, I can factor to 3, leaving behind a p minus 2. The orangish reddish, I can factor to 2, p squared minus 3p plus 2. And the pink I can factor to 2, give me 5p squared minus 8p minus 4. I can go ahead and factor these guys further because they're quadratic trinomials. So these guys stay the same, 5p plus 2, 3p minus 2, 2. Now factoring the yellow gives me a, p minus 2, p minus 1, and factoring the blue gives me 5p and p. That would be a minus 2 on the right and a positive 2 on the left. Now that everything's factored, you can go ahead and just cancel a whole bunch. So obviously the 3's will cancel, the 2's will cancel, the 5p plus 2's will cancel, the p minus 2 will cancel. So all that's left over is the p minus 1 over p minus 2. Factor and cancel, that's what you need to do. When it comes to multiplying and dividing, I actually don't want you to multiply and divide, just factor and cancel. But for number 12, which is a division problem, number 12, before I can factor and cancel, it needs to be a multiplication problem. Hopefully you remember from elementary school, your teacher telling you that every single time you divide, it's the same thing as changing this to a multiplication and then taking the reciprocal of the divisor. Then it becomes like number 11. Just go ahead and factor all the pieces that you can. You're going to factor this guy. You're going to factor this guy. I really can't do anything with the 2m plus 5, so I'm going to factor this guy. The yellow, it's a binomial, so all you can do is GCF. You can factor to 2, so that's 10m minus... No, you can factor to 4, excuse me. Factor to 4, so that's 5m minus 3. In the denominator, you can factor to 2, 5m minus 3. The 2m plus 5, you can't do anything with that, so it stays put. And in the reddish, orangish color, you can factorize him 2m and m. What is that going to be? 4 and 5? Nope. Yeah, 4 and 5. Yeah, so plus 5 here and plus 4 there. 8 and 5 makes 13. Start canceling whatever you can. 5m minus 3s, the 2m's plus 5s, and all of the 4 and 2 don't cancel out directly. You can still reduce them by 2's, so this 2 is gone, and this 4 becomes a 2. So all that's left over is 2 on top, and then m plus 4 in the denominator. That is as simplified as you can get. Number 13 is a compound or complex fraction. Lots of different techniques to simplify this. I'm only going to show the technique I like, which is clearing the fraction. To clear the fraction, you multiply every single term by the LCD. If you don't know what the LCD is, just by looking at it, this is the process you would go. You look at all the inner denominators, right? Not the big denominators, but the smaller denominators. And what I do is I write them vertically on top of each other. M plus 1, m plus 1, and 2. And what you want to do is factor everything if possible. Now, m plus 1, it's a linear factor. I can't do much with it, so it's just m plus 1. Notice how I grouped it in parentheses because they belong to each other. You can't split them apart. M is just an m plus 1, you can't do much. 2, you can't do much. So the least common denominator, you first look for common factors, and with everything written in front of you, hopefully it's very obvious to see that you have an m plus 1 in common. And then that's it. That's all the common factors. So for your LCD, you have to include the things that you did not circle. I did not circle a 2. I did not circle an m. So that's your LCD, 2m times m plus 1. What I'm going to do next is rewrite everything, but spaced out because I'm going to multiply. So 3 over m plus 1, space, plus 4 over m over m plus 1, space, plus 3 over 2. And then multiply every single piece by the LCD. 2m, m plus 1, 2m, m plus 1, 2m, m plus 1, 2m, m plus 1. And the idea is, if you did things correctly, that since we're using an LCD, all the denominators should cancel. M plus 1s cancels on the left, just the m's cancel out on the right, top right, m plus 1 cancels out on the bottom left, and just the 2's cancel out on the bottom right. And all that's left to do is multiply by what's left over. So we have a 3 and a 2m left over, gives us a 6m. Plus, we have a 4 times a 2 times an m plus 1 left over. Multiply them all together, you get 8m plus 8 over. In the denominator, we have a 2m left over. So if you multiply those two guys together, you get 2m squared. And in the bottom right, we have a 3 m and an m plus 1 left over. So if you multiply them all together, you get, 3m squared plus 3m. Then all that's left to do is to combine like terms. So we have a 6m and 8m like terms on top, 2m squared and the 3m squared on the bottom. So your final simplified result should be 14m plus 8 over 5m squared plus 3m. Technically, you would want to see if you can factor some more and cancel some more to simplify it, but nothing. You can still factor, but nothing will cancel out, so you can just leave it like this. That is as simplified as possible. Number 14 is just a linear equation. Nothing fancy about this. Again, lots of different ways to solve problems. I'm just going to show you one particular method, particularly if you have like difficulty with this. What I'd like to do is my tips are simplify first and then solve second. So I'd like to break down these parentheses via distribution. Just note that you're distributing a negative number in, not just a positive 7. So 6r minus 6r, well that's sort of trivial, but we'll take care of that later. Distribute the negative 7 plus 21r. Distribute the negative 7, minus 49, minus 28r. Next, I'd combine like terms on both sides. So, a trivial example, the 6r's are like terms, the negative 7 with the negative 49's are like terms, and then the 21r with the negative 28r's are like terms. So 6r minus 6r is 0. Let's do the reddish part first. 21r minus 28r is a negative 7r. And then doing the blues, negative 7 with the negative 49 is a negative 56. Let's add the 56 over, because, to solve for an equation, we want to move all the regular numbers off to the other side. 56 equals negative 7r. Divide both sides by negative 7, you get r equals negative 8. Number 15 is a linear equation as well technically, but you should notice we have special symbols here, absolute values. And before I can solve an absolute value equation, I need to get that guy by itself. So hopefully we can see by highlighting that we need to get rid of the plus 7 and we need to get rid of the 6. So this is just regular inverse operation, get rid of things that's farthest away first. First thing we're going to do is minus the 10. And then to get rid of the 6, we're going to divide out the 6. Giving us absolute value of 5n plus 3 equals, that's 7. Now how we handle the absolute value, well, we have a definition for it. Recall that absolute value of x will always give you one of two things. When you put stuff inside of absolute value, it will either give you the identical thing right back out or the exact opposite out. Now, it will give you the identical thing right back out if whatever you put into it is not negative. And it'll give you the exact opposite thing out if whatever you put into it is negative. Now, notice in our problem that we need to solve, the thing inside the absolute value contains a variable. By definition, we don't know what that variable is. It could be anything, hence we don't know if it's positive or negative. So as mathematicians, we sort of have to hedge our bets and consider both options. It is possible for this absolute value to give me the identical thing right back out, 5n plus 3, which, according to the original problem, should equal 7. Or it is possible it'll give me the exact opposite thing out, and to do the opposite you just wrap it in parentheses and stick a negative in front, which also equals 7. So now we have to solve these two linear equations. So let's solve the left equation. I'm going to minus 3 to both sides. 5n equals 4, and then divide out by 5, n equals 4/5. You can go ahead and work the right equation. You can distribute the negative in, or what I like to do is I like to divide out the negative 1 just so that my solving steps will be the same as the left equation. 5n plus 3 equals negative 7. That is to say, to solve for n, I'm going to subtract 3. 5n equals negative 10. Divide out the 5, giving you n equals negative 2. Now let's take a look at the equation before we apply the definition, this line here. Notice how the equation is just an absolute value equaling a simple number 7. If you have a simple equation like this, I mean, as good mathematicians should really check their answers always. But if you have a simple equation, if you trust your math, if you trust your arithmetic, whatever answer you get is most likely correct. The only time you really need to check is if you have variables on both sides. Number 16 was just a simple quadratic equation. I actually gave you a hint. I said it was factorable, so we can solve it by factoring. But honestly, I don't really care what method you use. You could use completing the square or quadratic formula if you wanted to. But the idea is to solve a quadratic equation, it needs to equal 0. So our first step would have been to subtract the 2x over. 3x squared minus 13x plus 14 equals 0. And this should be factorable because that was my hint, solve by factoring. So go ahead and factorize this guy. 3x and x. 14 would be 1 and 14, 2 and 7. So it needs to add to a 13 in the middle. So that's 6 and 7. So it would be 3x minus 7 and x minus 2. Now, the reason why we want to factorize them is because we now have a multiplication problem. This parentheses times this parentheses equals 0. That is key, the equaling 0. The zero product property says if you have a multiplication problem and equals 0, then each individual factor themselves can equal 0. Now it gives you two linear equations, easier equations to solve, hopefully, I think. So the left equation, you can go ahead and add 7 to both sides. Give me 3x equals 0, 3x equals 7, and divide by 3, 7/3. Here, add 2 to both sides, x equals 2. Number 17 looks wickedly scary and complicated. It's a rational equation. Lots of different methods and techniques to solve rational equations. The technique I like is clearing the fraction. And to clear the fraction, we need to find the LCD. And again, if you can't know what the LCD is by just looking at it, go ahead and write down the denominators on top of each other. B squared plus 6b, b squared plus 6b, so they'll be the same, b plus 6, and then go ahead and factor everything. b plus 6, b plus 6, b plus 6. LCD, hopefully it's very obvious. You have a single b in common, and you have the binomial b plus 6, and everything is circled, so that's our LCD. I'm going to rewrite the problem, giving myself some space, and with the denominators factored, so it's a little bit easier to see the cancelization. So rewriting the problem with everything factored, 2 over b plus 6, give myself some space, plus 3b squared minus 21b plus 30 over b squared, rewrite it in factored form, b plus 6, gives myself some space, equals 1 over b plus 6. So you're going to multiply everything by the LCD, b plus 6, b plus 6, b plus 6, and the idea is all of the denominators should now cancel. In the left fraction, everything cancels out. In the right middle fraction, everything cancels out. In the right fraction, only the b plus 6's cancel. So all you're left with is a 2 plus all of this mess, 3b squared minus 21b plus 30 equals 1 times b, which is just b. Notice it's just a quadratic equation, so gather everything to one side. I'm going to subtract both sides by b, and at the same time combine like terms. So that's going to give me 3b squared minus 22b plus 32 equals 0. And then you just go ahead and, solve it. It's a regular quadratic. Solve it by factoring, completing the square, yada, yada, yada. I think this guy's factorable. 3b and b, so I got a 32 here, 1 and 32, 2 and 16, 4 and 8. needs to add to a 22 multiplied by 3. There we go. So this would be a minus 16 minus 2 here. That would give me 22. And then we get 3b minus 16 equals 0. B minus 2 equals 0. So you get b equals 16 thirds. B equals 2. Now, when it comes to absolute value equations, I gave you stipulations on when to check your answers. When it comes to rational equations, you really don't have a choice. You always have to check your answers, but you only need to check against the denominators, because we do not want our denominators to equal 0. So here are the denominators again. B times b plus 6, b plus 6, and just a regular b plus 6. Our two potential answers, you have to check against the denominators. We do not want them to equal 0. If any possible answer makes any part of the denominator equal to 0, we have to throw them away. I hope you guys can see that all of our answers are positive, all of our denominators are plusing, so it's impossible to equal 0, which means these two answers are good answers. Last but not least, number 18, radical equations. Just like with absolute values, square roots are special symbols, so before I do any solving, I want to get the special symbol isolated by itself. In this particular example, he's already isolated, so I can go ahead and dive into solving it. Get rid of the square root. Opposite of a square root is a square. I saw a lot of people make this mistake. Oh, I'm going to distribute the 2, so that's x squared plus 4. This is bad. You cannot use the power property of exponents if there are pluses or minuses on the inside. You actually have to write it out twice or use the special pattern. Either way, this should be x squared plus 4x plus 4. So this should be the left side of the equation. So we have x squared plus 4x plus 4 equaling, when you square root, the radical goes away. So it's just a regular 4x plus 104. Notice it's a quadratic equation, so you go ahead and bring everything to one side. Minus the 4x, minus the 4x, minus the 104, minus the 104, minus the 104. You get x squared, these guys are gone, minus 100 equals 0. Now this is actually a special situation. Notice that you only have one variable term, the x squared, but you also notice they're perfect squares as well. So we can actually factor this using the difference of two perfect squares pattern. Or, since there's only one variable term, you can just solve it straight up using good old-fashioned inverse operations. Either way will get you the same answer. Since I've been factoring all day, let's just solve this straight up. Which means I want to move all the regular numbers onto the other side. So we'll go ahead and add 100 to both sides. X squared equals 100, and then to get rid of the square, you got to take the square root. Notice we are doing the blue. We took a square root to solve an equation. Every single time you solve an equation using a square root, your answer will be plus or minus. So we actually have two answers here, positive 10 and a negative 10. And let's take a look at our original equation before the squares. Notice we have x's on both sides. Just like with absolute values, that usually means we must check our answers. So go ahead and check. When you check your answers, x equals 10, you have to check it into the equation before you squared both sides. So we're going to check it into the original equation here. So plug it in. You get 12 equals 40 plus 104 is 144, and indeed 12 equals 12. So 10 is a good answer. Let's check x equals negative 10. You get negative 10 plus 2 equals square root of 4 times negative 10 plus 104. You get negative 8 equals negative 40 plus 104 is 64. And you get negative 8 equals 8, which is a false statement. So you have to reject negative 10. This problem only has one solution, positive 10.